All right, so suppose we can get an unbiased estimator for a parameter of interest. The next question is, how good is that estimator? So there's a notion called efficiency. What we are really interested in is not just finding an estimator, but finding an estimator where there's some guarantee of it being close to the actual value of the parameter. Now, of course, we know that the expected value is the, if it's unbiased, is the value of the parameter. But we might ask, how widely are the measurements of our estimator going to vary? If there's a small variance for our estimator, then that means we have some guarantee that their particular measured value is going to be close to the parameter. But if it has a big variance, then it's going to be not so useful. So we want an estimator theta hat with small variance. We should say an unbiased estimator, because if it was biased, then we wouldn't be getting close to our parameter in the first place. But we want an estimator with small variance. Now, there is a very important result here, which says that there is an absolute bound on how good we can do in this regard. So let me say theorem. So this is the cramer-rao inequality. And it says that that if theta hat is an unbiased estimator for theta, you know, let's say describe, and let's say our variables or population, really, I guess I should say, population described by some f of, let's say, x theta. So this is a probability density function depending on x and our parameter theta, which is continuously differentiable. So you have to be able to take derivatives with respect to theta, and those have to be continuous, and it's continuously differentiable. Then the variance of our estimator is at least 1 over n times the expected value of the derivative of the log of our density function with the random variable applied to it, divided by d theta squared. Okay. So let me just say, just very briefly, like just a bit to motivate this, although I will withhold the proof and give you a reference to another great video that has it by Professor Kontorovich. But yeah, so what's the idea here? This this denominator is supposed to be, so this is called the Fischer Information. And it's supposed to represent the possible information about theta obtainable from n measurements. And so let me just say a little bit kind of motivationally about why taking the derivative of something like this has, with respect to theta, has something to do with how much information is contained in your measurement. Okay, so this is just very motivational for a moment. So so the idea is we want to ask the following question: if we observe a value, capital X equals, let's say call it little x naught, for example. If we observe that our random variable is some x naught, how much information does that tell us about this parameter theta? Okay, so well, the idea is that our function, probability density function at x naught, is going to tell us something about how likely it was, in some sense, to measure the value x naught. Of course, this is all, continuous and whatever, but just morally speaking, this is telling us something about how likely x naught was. Now, of course, this is also a function of theta. And so, so if this doesn't depend on theta, then what that's telling us is that knowing that capital X is x naught doesn't actually tell us anything about theta. In other words, the observation of observing x naught was no more or less likely if theta was one thing compared to something else. And that means that we don't gain any information about theta. So to get information about theta from observing a measured value x naught, we really want to know how this density function changes as theta changes. So morally speaking, this sounds like something like taking the derivative with respect to theta. It happens to be that that the right answer, the one that contains the useful useful inequality, is by taking the derivative of the logarithm instead. So this might make some sense if you've seen a little information theory. This it's kind of where measuring something like how many bits of information you're given at the end of the day. And but in any case, so okay, just motivational though. So now, of course, we don't actually know what value we're going to observe. We're going to make some sort of a measurement, and we don't know what the value of that measurement is going to be. So instead of looking at exactly this quantity, we have to say, so this is somehow the information, let me call this informally, something about the info of measuring x naught. Actually, in fact, squaring it turns out to be the right thing about the information in x naught. Okay, but this is just motivational, right? So okay, but we don't know what value we're going to measure. So instead, we're going to replace this by what do we expect to find? So we want instead to say what's the expected value of this, where instead of looking at a particular value, we're letting this be the random variable. And this is what's called the Fischer information. So this is I of theta, the Fischer information. So from this point of view, what the cramer-rao bound says is that the and then of course the n is because you're making n measurements. So what this is telling you is that the more information that you get by taking measurements, the smaller you can make the variance. And in fact, this turns out to be a nice tight bound. So so let's say definition: an unbiased estimator theta hat of theta is is minimum variance if no other estimator has smaller variance. Is no larger than that of any other unbiased estimator. And so we find that the following useful result, which is that theta hat is minimum variance if its variance is this cramer-rao bound, is 1 over the information. So finally, we can now discuss like the absolute efficiency of some unbiased estimator. So if we have some unbiased estimator theta hat, then we say that the efficiency of theta hat, well, it's the ratio of the theoretical limit of how small the variance could be, 1 over n times the information of a measurement, divided by the actual variance of our unbiased estimator. So because this thing is the minimum possible value, the denominator is always at least as big as the numerator. So the maximum this could be is 1, and in general it'll be somewhat less than 1, which says something about what's the kind of ratio of the variances, right? Okay, so that's the notion of efficiency. Now, we should remark that this that to define this information, we took some derivatives. We had to assume that things were continuously differentiable. This doesn't happen for all of distributions of interest. For example, if you have a uniform distribution on some interval, this has some discontinuities on the edge, which translates, when you're talking about it as a function of x and the parameter theta, to a non-differentiable function. Okay, so we can't use the definition that we've just provided, for example, to describe this information. So it's also useful to have a notion of relative efficiency. So the relative efficiency of two different unbiased estimators is going to be the ratio of the variance of one to the variance of the other. Variance of theta 1 hat over theta 2 hat, this is the relative efficiency. Now, of course, we think about this variance as kind of so if I'm measuring the efficiency of theta hat, notice that the variance of theta hat's in the denominator, because it's kind of inversely proportional to the efficiency, right? That's the point. So like this expression, having the variance of theta 2 in the denominator really means that somehow the efficiency is in the numerator. So this is called the efficiency of theta 2 hat relative to theta 1 hat. So I'm just remarking it's kind of reversed from how they're sitting in that fraction. All right. So in other words, if this efficiency is small, that means that theta 2 is less efficient than theta 1. If this ratio is big, then theta 2 is more efficient than theta 1.